Okay, let's do a share screen. Yeah, it actually is working. Very nice. Okay, so we continue our discussion about cosmology. So as we said, modern day cosmology, right? So first, cosmology is the study of the universe as a whole, not the study of a certain subject, of a certain object in the universe. And for the universe as a whole, we derive the Robertson-Walker metric, which is a solution to Einstein's equation under the assumption of homogeneous and isotropic universe, which is an assumption that we believe is correct on the very large scale. So the Robertson-Walker metric, ds squared is minus dt squared plus a squared of t times dr squared over 1 minus k r squared plus r squared d omega squared, where k is the curvature, which can get three values, minus 1, 0, plus 1 for an open, flat, or closed universe. And that determines the spatial structure of the universe. A of t is the scale factor, which is determined by solving Einstein's equation. G mu nu is 8 by g t mu minus lambda g mu. And that gives two equations, which are known as Friedman's equations. A dot dot over A is equal to minus 4 pi g over 3 rho plus 3p, and A dot over A squared is equal 8 pi g over 3 rho minus k over A squared. These are Friedman's equations. Which are derived directly from Einstein's equation. And they determine the evolution of the scale factor, which multiplies all the coordinates. And so the evolution depends on, three things: on the k, right, the curvature of the universe, rho, and p, the energy density and matter density, which are related to each other by the equation of state. Then we spoke about the Big Bang, which is the time sometimes in the past where A of t was equal to 0, which means that all the spatial parts of the coordinates shrank to 0. That does not mean that the universe was necessarily finite. It could have been infinite, because infinite divided by something is still infinite. But everything was so dense that everything came down to shrank into an infinitely dense universe. We'll discuss about that shortly today. And then we spoke about the future. Of course, all the laws of physics that we know of are not valid at this point. So we just have to invent new laws or to try to guess what might have been happening there at that time. But shortly afterwards, then we believe that the laws of physics are valid, and we're actually trying to mimic them in laboratories, especially in CERN, when we're trying to get to higher and higher energies. We'll discuss that today shortly. Then we spoke about the future evolution. And we saw that there are two options. For an open and flat universes, the universe will continue to expand forever. While for a closed universe, the universe will essentially shrink back. For a closed universe without a cosmological constant, the universe will eventually shrink back to a single point, and everything will get smashed together in a big crash. As far as we know, from the measurements we have today, there is a dark energy, cosmological constant. And so we do expect the universe to expand forever, unless, since we don't really understand this dark energy, unless sometimes in the future, the equation of state will revert back and we get a negative energy, which will attract back the universe. So this is something which we don't know. To the best of my knowledge, nobody knows. Certainly I do not know what will happen about that. Then we spoke about the cosmological redshift. So we said that since the universe is continuously expanding, A of t changes with time. And so when we speak about the proper distance between two objects, it changes with time. Even though the objects are co-moving, namely they are stuck to the same place in the coordinates as they were, the distance between them grows. L of t is just L0 A of t, right? Which is linearly proportional to A of t, right? And the way to think of it, right? There are two observers. They're not moving, right? Could be two, well, let's be a little bit more realistic. There are two galaxies. Right, and the distance between, they're not moving anywhere, right? But the grid is moving, is expanding. Right, so this galaxy here, this galaxy here, this one, two, here, right? So the proper distance between them is changing with time, but not because they are moving. And because of this change, any observer on one galaxy will view the other one as being receding away from it at the velocity delta v, which is a dot over a delta L. Where delta L, right, is just a t delta r. Right? This is on the coordinates, right? This is delta r between them. And so because of that, we have shown that if there is a radiation signal, which is measured with having a frequency omega, then the observed frequency, right, delta omega over omega will be just minus delta A over A, or omega of t times A of t is constant, which means that if a photon is emitted with frequency omega 1, it will be observed with a lower frequency, omega 0, is omega 0 over omega 1 is just A1 over A0. Omega 1 is just emitted photon frequency, and omega 0 is just observed photon frequency. And that is representing the fact that the universe had expanded from the time of emission to the time that the same photon was observed. Right? So this very much resembles a Doppler shift. So that's why it's called a redshift, the cosmological redshift. Right? Or Z, it's the same notation as the gravitational redshift. So it can be a bit confusing, but we're talking about two completely different things. And that Z is defined as the ratio of the observed wavelengths minus the emitted wavelengths divided by lambda 1, which is A0 over A1 minus 1. Now note that this is although the derivation is very similar to the derivation of a Doppler shift, it's not really. And a key difference is that if you have a Doppler shift, it's only between two moving objects. Here, the objects are not moving at all, simply because of the fact that the scale factor, changes with time. Noise. I'm not sure who is responsible for this noise. I'm going to turn your mics off, because otherwise I cannot turn my mic off without stopping the class. Okay, I think it stopped. I muted one of you. Can you hear me? Okay, good. Okay, so the redshift really replaces, the cosmological redshift really replaces time. Rather than saying an event happened, that and that and that time ago, million years ago or billion years ago, we studied a coordinate redshift 1, 2, 3. I mean, as you can see, when we say a redshift is equal to 1, that means that the redshift was half the size it is today, right? Okay, the important thing is to notice that this is not the same as the Doppler rules. That's the key here. And then the last thing we did was to show that essentially the same thing can be said about motion of gas. So massive particles, not just photons. And when we did the calculation, we found that the momentum P for massive particles V over square root of 1 minus V squared is also constant divided by A. So massive particles, essentially gas, right, that flow in the universe, do slow down because of the expansion of the universe. All right, this is as far as we managed to go to last time. Any questions before we start the new stuff? Okay, you can turn your mic on if you have questions. Any questions? And again, I do ask everybody who can and feel comfortable, please turn your camera on. I think there are some students that I never saw how they even look like. So please do that. Any questions? No. If not, then there are a few important topics which we have not discussed yet. So now it's time to discuss them. So the first thing of interest is, how do we measure distances in the universe? Right. How do we, that's a very crucial thing, which we kind of touched upon. I mean, we have a universe that expands, right? It's not constant. So how do we know the distance to another galaxy? How far is it, the other galaxy, from us? When you think of it, it's not a trivial question at all. When you have a universe, essentially a manifold, that constantly changes, right? So how far is that? How do we even define distance to in an ever expanding universe? Any suggestions?
A simple thought would have been trigonometry, but it doesn't feel that simple.
Yes. Okay. No, that's a very good direction. We can use geometry, and first, it is really not that simple. And because it is not that simple, in fact, there is more than one way of defining a distance, apparently, when you think of it. But before we even do that, we note that when we speak about co-moving distance, right? The distance of galaxies that are stuck to their coordinates is not even necessarily useful in some basic sense, right? Because we can't even measure it, right? At the end of the day, we are measuring mostly, well, yeah, mostly photons, right? So we're interested in knowing where these photons originated from somehow, right? So we can define something which is motivated by geometry, which is called the luminosity distance. That's important because, you know, in cosmology, because of that, there is no such thing as a distance really. There are various types of distances. So the first type that we talk about is a luminosity distance, right? It's called dl, and is defined such as dl squared is just L over 4 pi f. So L is the luminosity, or the absolute luminosity of a source. And F is the flux, which is measured by us. Which is essentially energy per unit time per unit area of the detector. Now, the flux is something which we measure, right? We put a detector, can be our eyes, and we're seeing that many ergs coming per second per centimeter square, right? We put a satellite or something, you know, we know that the area of the detector of the satellite, we know how many photons reach it per unit time. And this is something which we measure. L is something which we don't necessarily measure, but we hope that there are some objects which we call the standard candles, which we know how much energy they emit per unit time, right? Luminosity is energy per unit time, right? And essentially this comes out from the fact that if the universe was flat, Euclidean, that's exactly how would be, and the emission was spherical, right? This is exactly what we would call the distance, right? Think of a lamp, right? You have a lamp. Now, the lamp emits, you know, you have a, let's say, a strong lamp and a weak lamp, right? You can have a weak lamp of 60 watts energy per time, right? Or a stronger lamp. Now, if you put a stronger lamp, now assuming that the lamp emits, you know, spherically, putting a stronger lamp in a further distance, you'll see the same amount of energy, the same light essentially, the same flux. And that's the right measure, right? So this is true if the universe had been flat, right? Okay, so you know F over L. So for flat universe, F over L is just 1 over the area. So it's just 1 over 4 pi d squared. Just for flat universe, I can say d. Okay, that actually manifests the importance of what we call this standard candles in astronomy. In fact, one of the hardest questions ever, I mean, you know, throughout the history, was to identify how far a source is it from us. That's one of the most important questions in astronomy in general. You're seeing something, how do you know that this something is you know, something weak and close, or very bright but very, very far? It's not a trivial question at all. Now, when we speak about the Friedman-Robertson-Walker metric, right, obviously the flux is going to be diluted relative to a flat metric. Right? And for W metric, flux will be diluted. Right? Why? Well, let's say we have a source. The source emits photons. Now we're really making a sphere around the source, right, at some distance dl. So all the photons that were emitted from the source will eventually cross the surface. The number is conserved, right? And if the sphere is at co-moving distance r, so maybe I should not say dl, I should say co-moving distance is r, right? Then the physical distance of the sphere, b, is a0r. And of course, A0 is the scale factor of the photons when they are observed, which is now, right? Now, but we have a dilution of the flux by two other effects, right? The first one is that when we look at an individual photon, they are being redshifted, right? By a factor of 1 plus z. So each individual photon is redshifted by 1 plus z. So its energy as we see it is less than the energy that it had when it was emitted, right? And also the photons hit the surface of this sphere less frequently than they were when they were emitted, right? Because if they were emitted at a separation of delta t apart, right, the delta t crossing, right, is just times 1 plus z delta t emitted, right, because the sphere expands. So overall, what we're going to get is that F over L is just 1 over 4 pi. We said D is just A0 squared R squared times 1 plus Z squared. From which we get immediately that the luminosity distance, dl, is just equal to A0 R times 1 plus Z. Okay. Now, okay, we can measure dl, right? Not directly, if we know what is the luminosity of an object, of the standard candle we're interested in. We know what is the observed flux. This is the same that we actually measure. Then just by plugging into this equation, then we have the luminosity distance. And the luminosity distance is related to the co-moving distance r, to the scale factor A0 and to Z. Right? Now, R, of course, is not something which we can measure. So we somehow have to remove it, and I'll do that in a few minutes. But before I'm going to do that, I want to mention another possibility of measuring distances. So there is more than a single option. By the way, any questions about the luminosity distance? Questions?
I have a question.
Yes.
If we already know that measuring the redshift is basically just another way to measure time, why don't we just consider just getting what the redshift is? if we know how, if we can scale the redshift itself, then we'll know how much time had passed, and then we can just say that in natural units distance is equal to time.
I guess you can, but R here is the co-moving distance, so it's how we put the coordinates really. Right, so it's basically our arbitrary choice of coordinates.
I see.
And the redshift, yeah, I can replace the redshift with time. It's just more convenient to work with redshift. So everybody is using that.
I see.
Okay.
Yes, thank you.
All right. So any more questions? Okay. Now I said this is not the only way of measuring distances, right? There is another observable parameter, which is useful in two cases. One of them is when we have a nearby big object, such as a galaxy. Another one is cosmic microwave background fluctuations, which I don't know if we'll discuss it today or on Thursday. And that's called the angular distance. Or angular diameter. So let's say that I have a physical object which is quite big. So let's say I have a big galaxy nearby, right? And it has, let's say it has some physical size. D. That's the actual size of this galaxy. Okay? And it emits photons from both edges. And both of them are observed by me. Right? I'm sitting here and I'm seeing these photons. Maybe I'm not sitting here, maybe I'm sitting here. Ah, I'm just a lousy drawer. Now, both photons were emitted at the co-moving time T1. Right, this is the time co-moving time that the photons were emitted. They are observed, right, at time T0, of course. Now, let's say that I'm seeing, you know, the angle here would be delta. Right? And let's say the delta is very small, right? So I can say for small delta, observing angle, then of course the D, just by trigonometry, right, is R times A of T1 times delta. So now we can define the angular diameter distance which we denote by dA, which changes with redshift, via the relation, right? Delta is just D over delta, dA. So dA of Z is R times A T1, which is A0 times R times 1 plus Z minus 1. Because AT1 is A0 divided by 1 plus Z. So when we compare those two, then we immediately get that dA and dL are not the same, but rather dL is equal to dA times 1 plus Z squared. So we can try to measure distances to galaxies in two different ways. We get two different results, and there is no right or wrong here. It's just the method that we're using. Now, for nearby galaxies, it really doesn't really matter that much because Z is very small. It is becoming important when we spoke about the cosmic microwave background, which is quite far. Okay, there are other methods, but I skipped them because I think they're much less useful. These are by far the two most useful distant measurements in the universe. And I guess the most important part is to pay attention and realize that when we say distance, there is no such thing as a simple definition of a distance in an expanding universe. Okay. Now let's go back to the problem of expressing the luminosity distance, not in terms of R and A0, which are not measured, but only by only using terms of quantities which can be measured. So express dA using measurable quantities. Right. How do we do that? Right. So we start from the FRW metric on an algeodesic. Zero is ds squared is minus dt squared plus a squared of t divided by 1 minus kr squared dr squared radial geodesic. So I omitted the omega. So you can simply take a of t to the left-hand side and get that integral from t1 to t0 of dt over a of t is integral from 0 to r1 of dr over 1 minus kr squared minus 1 to the power 1 half. Okay, just sounds trivial. This is a basic integral, right? Which you can immediately do. That is just 1 over sine of r when k is equal to plus 1. What is that when k is equal to 0? What is the integral on the right-hand side when k is equal to 0?
That's R1.
Yeah, that's R1. And when k is equal to minus 1, this is just a sign equal case. Minus 1 of R1 and k is equal to minus 1. So this is something which we can solve immediately, right? Now, if the galaxies are not too far, we can use a Taylor series to expand A around its present value. And so use Taylor expansion. Valid for galaxies not too far. Right. A of T1 is A0 plus A dots 0 T1 minus T0 plus 1 half A dot 0 T1 minus T0 squared plus right? That's just a Taylor expansion, which is written as A0 plus A dot over A 0 T1 minus T0 plus 1 half A dot over A 0 T1 minus T0 squared. All of that. Yeah.
Can I ask a question?
Yes.
Why do we assume that to do the Taylor expansion, if we need to do Taylor expansion, then we assume that the change is small, right?
Yeah.
However, if we assume that A is uniform all across the universe, then for small time changes, the distance between one point and another doesn't really matter, right?
We are doing integration here from T1 to T0 of dt over A of t.
Yes, but why do you have to assume that the galaxies are not too far from each other?
Otherwise, I cannot use. Otherwise I cannot use a Taylor expansion basically. So not too far from each other, not too far from us.
Yes, but it's the same. But it's the same A on this galaxy and the nearest galaxy, and also on a galaxy far away, right?
But right now we are just looking at you can think of a single galaxy which is not too far.
Okay.
Okay, I'm just doing a Taylor expansion. Don't get it to places where it isn't. Okay, just a Taylor expansion right now. I said, okay, if A is not changing too much, right? I can simply use A at time T1. It's just Taylor expansion A0 plus A dot times T1 minus T0 plus half A dot squared A dot dot times T1 minus T0 squared plus blah blah blah.
Okay.
I'm just justifying the Taylor expansion used here. That's all. Nothing more than that. Now, of course, this should ring a bell because this is A0 times 1 plus A dot over A today is what?
It's the Friedman equation?
No. What is A dot over A? Right, plus, sorry, so the minus would be now. Minus 1/2 Q0 H0 squared T1 minus T0 squared plus extra terms. Of course, H0 is Hubble's constant. Today. And Q0 is the deceleration parameter, which we introduced, right? Is just a minus A dot dot over A dot squared. And again today. Right? You remember that, right? Oh, come on. Okay. So now, after writing that, we go back to this equation here and can write down again a Taylor expansion. So on the right-hand side, we, for R, which is not too big, we can simply stick with an R because 1 over sine would give us an R. So we're going to get with using this here, and this equation will lead us to R is equal to 1 over A0 times T minus T0, sorry, T0 minus T1 plus 1/2 H0 T0 minus T1 squared plus blah, blah, blah. Okay, do you see that? I just, again, use a Taylor expansion. I get the 1 over A0 times 1 plus H0 T1 minus T0. So I just plug it into the integral. I only use these first two terms really. Put it in the denominator of the integral. 1 over A0 goes out. I have integral of dt minus H0 T1 minus T0. Integral of dt of that. That's how I get back to this equation here. Yeah? Wait a second. You say that it's not there's nothing really more than a Taylor expansion here. Then,
This is specifically for k equals 0?
No, actually true for any k. Because you can do it also for 1 over sine of r.
Yeah, it doesn't make like it doesn't like the solution for the integral on the left hand side will be the same no matter what the solution on the right hand side is, right?
Right. Yeah.
Yeah. Okay. Thank you.
Now, since what did I do here? Right. Since now use the fact that 1 plus z is a0 over a t1, then we have from this equation here, a t1 over a0, that is just 1 over 1 plus z. Then we have 1 over 1 plus z is equal 1 plus h0 t1 minus t0 minus 1 half q0 h0 squared t1 minus t0 squared plus extra terms. So for small, again, using again h0 times t1 minus t0 small, so we can again do a Taylor expansion. We can write that as 1 minus z plus z squared. And again, we ended up writing that as t0 minus t1 is 1 over h0 times z minus 1 plus u0 over 2 z squared plus extra terms. I'm doing plenty of Taylor here, but there is no more than that. Right? I don't think there is a need for me to go through all the details here. This is something which you can easily complete by yourself. And if you cannot, then it's your responsibility to let me know that there is a problem here. Okay. So this, we can now finally plug these results back into this equation. And so we end up with R equal 1 over A0 H0 times Z minus 1 half 1 minus Q0 Z squared plus other terms. And the final thing which is left is to write down DL. We'll use the fact that as we wrote down the luminosity distance as A0 times R times 1 plus Z. And that leads us to DL as H0 minus 1 times Z plus 1 half 1 minus Q0 Z squared plus extra terms. Which is what I promised you, is an expression of the luminosity distance only in terms of measurable quantities. Now this equation has a name, but you actually know the name. Do you know how we call this equation? Anybody want to guess?
Hubble distance?
Nearly. This is Hubble's law. Because this is exactly what Hubble did, essentially. Right, back in 1929, so nearly 100 years ago, right, he measured the distance to galaxies, and he measured the redshift, and he discovered this law, that the distance is proportional to the redshift. In fact, just a few minutes before the class, I went over to the web. Let's see if I can find it. And there you go. This is a replica, I guess. It's from the universe today, of the original Hubble's law. Right? He measured 24 galaxies. Of course, this is 1929 technology that was valid about 100 years ago. And he found this correlation, which is, of course, 1 over h, Hubble's constant. It's actually something which he measured. Of course, today we have many more advanced tools than he had. And he had it very, very precise. So we can see that the universe is not only expanding, but it's accelerating. But it doesn't matter for the sake of scientific argument of this achievement. All right. So this is Hubble's law. Essentially what Hubble's law tells us, so what he did is measure the redshift and the distance to sufficient number of galaxies, and then he could deduce the value of the Hubble's constant, h0. That's how it's being measured. And the second order effects would give us the deceleration parameter, Q0. But that depends, of course, on the quality of the measurements that you have. All right? Questions? So by being able to identify the distance to galaxies, which is an interesting story by itself, how it's being done. I don't know if this is the right place to speak about it. The redshift is something which is relatively easy to determine. This is based on spectroscopy, indeed, spectral lines. Distance is much more difficult, but can be done if you have standard candles, which you did have. That's back to Henrietta Leavitt, an astronomer back in Harvard about 100 years ago, which found these Cepheids, changing stars, which correlate between the variability time of the star and the luminosity. And Hubble's discovery was that one of the discoveries of Hubble was of Cepheid stars in the Andromeda galaxy, which was the first proof of a galaxy outside of the Milky Way. Till then, galaxies were not known to exist. Okay. Questions? No. Okay. The next thing we're going to do is to look at the evolution of the scale factor, namely the evolution of the universe. So, essentially what we're up to is solving Friedman's equation, right? So if we have A dot over A, Friedman's equation, A dot over A squared is 8 pi G over 3 rho minus K over A squared. This is the second Friedman equation. Which we want to solve now and get the evolution of A of t. Now, of course, that depends on the scenario at hand. What is K? What is rho? For now, okay, we're going to stick to K equal to 0, which is the simplest case. We can just write down this equation can be solved. for the scenario of interest. Now remember that we showed 1 or 2 lectures ago, right, that depending on the ingredient of the universe, the equation of state always have the form of P equal to omega rho, right? That after conservation of energy, we ended up with, so conservation of energy, that rho goes as a to the power 1, 1 plus omega times -3. So P equal omega rho gives rho proportional to a to the power -3, 1 plus omega. And we said for the different possibilities that we know of the universe, we have matter dominated, rho m goes a to the -3. And so that means that omega is equal to 0. Rho radiation is proportional to a to the -4. That is omega is equal 1/3. And rho vacuum is proportional to a to the power 0, which means that omega is equal to the -1. For the 3 ingredients of the universe: matter, radiation, and vacuum. Right. So looking at that, we find that, for example, that rho matter, the energy density of matter, as it changes with time, just rho matter today, times a0 over a of t to the power 3. Right, so we can write it down as the rho critical times omega matter times 1 plus z q. Yeah, you all with me? Since rho changes, now I'm interested in the way that the rho changes with time. So I'm looking at rho matter as a function of time, right? It's rho matter today. Since it is proportional to a to the -3, then it's just a0 over a to the power 3. But rho matter, I can write down at rho critical times omega matter. This was the definition of omega matter times, and a0 over a is just 1 plus z. So just 1 plus z cubed. And omega matter, just to remind you, omega matter was rho matter today divided by the critical density. The critical density, right, is today is 3h0 squared divided by 8 pi g. Now we can do the same for the other ingredients. Right? So this is for the matter. But we also have for the radiation. Rho radiation is a function of time, right? Is rho radiation at today times a0 over a. What power will be here?
It's the power of 4.
4, of course. Thank you. So this is rho c times omega radiation times 1 plus z to the power 4. And what about the vacuum energy?
It would simply be constant.
It's constant in time, rho lambda. Now we can refer back to observations. So we know that observations, and I mentioned that, so observations tells us that total omega, normally you know it simply by omega, is how much? Do you remember? What is omega total?
1.
It's 1.
1.
It's 1. And the matter? An omega matter is approximately 30%. So, sorry, 0.3. Approximately. Slightly less, but it doesn't matter. And omega radiation is 8.2 times 10 to the minus 5. So very, very small. And most of the energy in the radiation actually originates from the cosmic microwave background. There is some, of course, energy in the photons that the sun emits. It's very small. So today we have that omega matter is much greater than omega radiation. And of course, omega lambda is greater than both of them. It's about 70%. But of course, this is not always been like that, right? Since omega radiation, so the energy density in the photons dropped down faster than the energy density of matter, right? Then there was some time in the past, in the past history of the universe, where the energy of the radiation was dominated the structure of the universe, right? The total energy of the universe. And it's pretty easy to know when it was, right? So we call it T equilibration. So at today, this is today, right? At some time T, which is T equilibration, right, in the past. Plus the corresponding would be scale factor A, which is A equilibration, or redshift Z, Z equilibration. Radiation and matter had equal energy densities. Now it's pretty straightforward to calculate immediately when this was, right? Since we know how omega matter evolved with time, we know how omega radiation evolved with time, right? Or the density. Then we immediately get that 1 plus Z equilibration, which is just a 0 over A equilibration, is omega matter over omega R, which is 3.6 times 10 to the 3. So at Z of 3600 and earlier, the dominant term in terms of energy of the universe was radiation, not matter as it is today. Now, how does the temperature of the radiation evolve?
I would assume in the same kind of law of black body radiation, no?
Exactly, very good. Like a black body radiation. And in the black body radiation, how is the temperature related to the energy density of the radiation?
Rho is equal to T to the power of 4.
Very good.
Times some constant.
Very good, very good. This is Stefan Boltzmann's law. So use Stefan with an F. Boltzmann law. T radiation goes to rho R, T to the 4 goes to rho R, which is proportional. So T to the 4 goes to rho R goes 1 plus Z to the 4. All right. So we know what was the temperature of the universe at that time. So T equilibration is equal to T0 times 1 plus Z equilibration. So what is T0? What is the temperature?
2.7 Kelvin.
Exactly, this is 2.7 Kelvin. It's a cosmic microwave background. Times 3.6 times 10 to the 3. That's about 10 to the 4 degrees Kelvin. 10 to the 4 degrees Kelvin is nearly 1 electron volt, 0.9 electron volt. So again, I hope you're seeing the picture. So I'm now talking about the history of the universe. And I'm saying that right now, the universe is cold, right? It's the energy density is mainly associated with matter. And the cosmic microwave background is represents a small part of the energy density. But when I go back in time, the energy density in radiation grew up faster. And so before redshift of 3600 or so, this energy density was the dominant term. And at that time, the universe was much hotter than it is today. It was 0.9 electron volt. Now we can go back to Friedman's equation, this one. All right. Now we know how the energy density looks like in a radiation-dominated universe. Let's assume for simplicity that k is equal to 0, so we don't get messed up with some more complicated formulas, but a computer can easily solve it. And so, okay, so now let's make a separation between the matter-dominated and radiation-dominated universe. So for matter-dominated, rho m goes as a to the minus 3, right? So I can simply plug in, right, a to the minus, I can simply plug in a to the minus 3 here, right? And then k is equal to 0, I'll just assume it's a 0. And then I can immediately solve this equation. And I end up neglecting everything else, right? Of course, it's a very approximate solution. So for matter-dominated universe, and k equal to 0, we have a of t is equal to 9/4 of 8 pi g over 3 omega m rho critical times a0 cubed to the power 1/3 times t to the power 2/3. It's actually pretty straightforward to see the time dependence, the 2/3 dependence, because when I put, rho goes as a to the minus 3, I'd have a dot square goes as a squared divided by a cubed to be a to the minus 1, so a dot goes as a to the minus 1/2. The a dt goes as a to the minus 1/2, that immediately tells me that it should go as t to the 2/3. Right? Because a dot would go as t to the minus 1/3, so it's a to the minus 1/2. Okay, this algebra should be quite straightforward, I hope. Guys, if any of you, I do expect you, listen, we're kind of running out of time in this course. I do expect you, I hope you're doing it all the time, to go over very carefully over all the detailed calculations. If there are steps that you don't fully understand, then complete them. Don't rely on some program to do it for you. Okay? Because it's a very good exercise in general. So that's for a matter-dominated universe. For radiation-dominated universe, we get Again, now it goes as rho goes as t to the minus 4. Again, k is equal to 0. We end up that A of t is equal. That's the guy. My apologies. The 9/4 is also inside of the parentheses. I did this calculation properly, but when I copied it to the whiteboard, now I copied it wrongly. When you do for radiation dominated universe, you end up that A of t is 4 times 8 pi g over 3 omega radiation rho c times a 0 to the power 4, all that to the power 1/4 times t to the power 1/2. So we said that this is true at early times. So this is when t was much more than t equilibration. Then the energy density of the universe was dominated by radiation. And so this represents this, two stars equation represent the evolution of the scale factor. And when t is much greater than t equilibration, then it's the first solution that represents the evolution of the scale factor. So it's kind of interesting because if we look at the t and a of t, the evolution of the scale factor, then it actually speed up. It started with a t to the power 1/2. Well, it started with some inflation, so I'm going to say a word about that here. Then it goes as t to the power 1/2. And then at equilibration, it switched to go as t to the power 2/3. Well, that's not the end of the story, because we said that there is also, in addition, a vacuum. So when we speak about the vacuum, then for vacuum dominated universe, then the energy density we said is rho lambda is lambda over 8 pi g. And then the solutions, now it's easier to obtain a solution for open, closed, and flat universes. I'll just hand you the solution. A of t is just for an open universe, it's sine hyperbolicus of lambda over 3 to the power 1/2. I think you might even derive that at a certain point in your homework. For k equal to -1, and then it's exponent of plus minus lambda over 3 to the power 1/2 t, for k equal to 0, and then it's a cosine hyperbolicus of lambda over 3 to the power 1/2 t, when k is equal to +1. Now, in fact, it's the same universe, just with different coordinates. And all of it has a name. These are all called the de Sitter space.
Can I ask? And in
Okay, I'm sorry, I cannot hear. There is
so happen to be that in the future, if we imagine that most, if not all, of the stars. Oh, now?
I'm sorry, there is a problem in your microphone or in the communication, so I cannot hear the question.
I'll type in chat then.
Okay, you can type in the chat. I cannot hear the question. So we said that today the universe is 30% dominated by matter and 70% by radiations, by vacuum. So we're pretty much at the edge of changing into the exponential expansion. Now let's see. Wouldn't the universe be dominated by vacuum in the future? Well, that's what we said, yes. If this whole theory is correct, and if nothing that we do not understand in the evolution, in the equation of state of the vacuum energy will not change in the future, then yes, it will be dominated, actually started to be dominated by vacuum energy in the future. I'm not sure that I understand the second comment that was written here, since all the stars would blow up. The stars would not blow up. One thing to remember is that we are talking about a metric which represents the universe as a whole. It is not valid for single stars, of course. When we speak about single stars or single objects, the valid metric is the Schwarzschild metric, or the extension of it to Kerr for rotation. That's called the Kerr metric. This solution is valid for very large scales, so scales of clusters of galaxies and above. Right, so nothing will really happen to the stars, nothing will really happen to the galaxy, but or to any of the galaxies. What will happen if this mathematically, if this math is correct and there is nothing that we're missing, and we're pretty sure that there is something which we're missing because we don't really understand this nature of the dark energy, then the very far distance away galaxies will continue to recede away from us in an everly expanding fashion, in an exponential expanding fashion. So in the future, we simply will not be able to observe any of them. Does that answer the question?
Yes, thank you.
Okay, and then I looked again. You might have seen this. Look, I told you I did a little bit of looking. This one. Yeah, I wanted to look at this picture. You might have seen tries to capture the mathematical essence of things. So you're saying there is initially there is kind of 1/2, which then continues to grow as t to the power 2/3 from the Big Bang until today. There's like 30.88 billion years, and now we're kind of transiting into dark energy accelerated expansion, which is something that happens very recently when we speak about cosmological times. All right, so that to give you some feeling of what we're talking about. We'll get back to that in a few minutes. I think today we can have time. Okay. Any questions? Any more questions about that? Okay, then the next thing that I want to discuss with you is the thing, observational evidence. So any theory, as we said, regardless how beautiful it may be, it may look like, if it is to be accepted as a physics, theory in physics, which represents the real world and not something which is mathematical, which may represent something beautiful imagination, it has to go through observational support. The theory itself, without the observation or experiment, is meaningless. So what are the observational evidence for the correctness of all these Big Bang theory? So it turned out that there are 5 independent independent measurements that support this Big Bang theory. And this is not trivial. I want to tell you that until the 60s, people were still debating whether this theory is correct or not. But right now it's pretty well established. Otherwise, I wouldn't call it a theory in physics. So there are 5 observational supports to the Big Bang theory. Does anybody want to guess what they are?
I assume that the first one is the actual observations of galaxies receding away from one another.
Very good. So the first one is Hubble's law. It's the first indication that the universe is not static and not steady. Yeah. What's
the CMB?
CMB, cosmic microwave background. What are the other ones?
Would the redshift be we would consider the cosmic microwave?
Sorry?
Would the cosmological redshift be considered as part of the CMB?
No, CMB is the cosmic microwave background. I'll say a few words about that shortly.
So we can talk. So another evidence could be the redshift.
No, not by itself. There was an alternative theory in the 60s that spoke about the creation of galaxies and the continuous expansion in an infinite universe. So no, it's not by itself, it's not.
Maybe observations of very distant galaxies. What?
Yeah, what about them?
Well, if they are very distant, I would assume that I would be looking very very far back in time. And if the Big Bang theory is correct, then very far back in time, the ancient galaxies would resemble much more clouds of dust, more than the well-formed galaxies that we know of today.
Excellent. Yeah, galactic evolution. You would be seeing younger galaxies. Indeed, you're right. That's one of the proofs. When you're seeing far, you're not seeing the same galaxies as we're seeing in today, in the nearby universe. The galaxies change their morphologies. They grow up, they mature, they get old, very much like all of us. So yeah, so you're seeing younger galaxies and they behave differently and they look differently than older galaxies. There are 2 more. Okay, maybe I should say. So one is called the primordial abundances of the light elements. This is something which you may not have asked yourself. We are made of atoms, right? All of us. Where did these atoms came from? Where did these atoms come from, by the way? We're made of carbon, we breathe oxygen, there is a nitrogen in the atmosphere. Where is it all coming from?
Well, the slightly heavier elements like carbon and oxygen would come from supernovae.
Yeah, they would come from stars. Yes, but what happens in stars?
The nuclear fusion.
Right, so hydrogen turns into helium, which turns into carbon, the CNO cycle, right? carbon, nitrogen, oxygen, etc. There are more elements that are being burned. Where did the hydrogen come from? Okay. And the last one is called the Baryonic acoustic oscillation. As you might have heard, these are fluctuations which are seen in the cosmic microwave background. Now let's start going over them one by one. The important thing here is that they're all independent measurements. So they don't rely on each other. What is what? Hubble's law. Well, I basically just showed it to you, right? This was the first indication that the universe is not static. So he made measurements. I just showed it to you, the 24 galaxies, which he managed to measure in his original, which he published in his original paper. He determined the radial velocity of 24 galaxies, which he could estimate the distances. The universe expands. That was 1929. By the way, Hubble never got a Nobel Prize. The reason is that at that time, the Nobel Committee did not consider astronomy to be part of physics. They've changed their mind. But the same year that he was supposed to get it, he died. It was quite sad. The CMB. Okay. What is the CMB? The cosmic microwave background, CMB. So what is the cosmic microwave background?
The leftovers from the Big Bang? Radiation.
Pretty much, yes, right? So the logic goes as follows, right? We said that as we go back in time, the temperature of the universe was higher, much higher than it is today, right? So there is a critical temperature, which is what? It's the ionization temperature. What's the ionization temperature of hydrogen atom? I'm sure you've seen that in one of your courses.
About 13.7 electrovolts.
Very good, 13.6. Good that you remember it. So the ionization energy of hydrogen atom, 13.6 electron volt. So when the universe was hotter than that, it's actually less than that, because we have enough photons at the high energy tail of the distribution to ionize all the atoms. That means that there could not have been any atoms present in the universe, right? Then what was there instead?
Just radiation.
No, there were
soup
electrons.
of particles.
Of course, there were electrons and protons, right? The electrons and protons could not combine to get hydrogen, because every time they tried to do that, some photon would interact and would just kick them off. So there were protons and electrons. If you go even earlier, then there were not even protons, because they were made out of gluons and quarks, and that's a different story, right? But at that time, when that we speak about, there were, before this, when the universe was hot enough, there were no atoms, but only electrons and protons. Now, electrons are great scatterers. So the cross-section for scattering is the Thomson cross-section. So there are a lot of free electrons. So in the early universe, there were a lot of free electrons. Which scatter the photons. Right? So the outcome, if you happen to be there, It would look like basically like driving through a fog or flying through a cloud. You wouldn't see anything because the photons were just, you know, constantly being scattered, and they didn't go very far, so you couldn't see anything really. Now, as the universe cooled down, right, as the universe expanded, it cooled down. When it cooled down, eventually, the temperature was low enough so that electrons and protons could combine to form the atoms, right? Now, this is called recombination. Although the name is misleading because it's really the first time that atoms were formed, not recombined. It's not the second time. When the universe cooled, protons and electrons formed atoms. It's called recombination. And then what happens once the atoms are formed? What happened with the photons?
They started just flying about.
Exactly. Now there was nothing to scatter them, so they just start to fly along the geodesics. And where are these photons? They keep on flying. And they're around us everywhere. This is the 2.7 cosmic microwave background that we're seeing. Okay. Of course, they keep on cooling down and they keep on flying around us. So these are relics of the early times before the atoms were formed. All right. So what we can see is that we can see that they are isotropic. Since then, photons flow freely. They form the CMB, which is isotropic. And that's 2.7 degrees Kelvin. Now this is 2.7 degrees Kelvin is 160 gigahertz, which is exactly in the microwave. So they were first detected in the 1960s. They were predicted in the 1940s by Ralph Alpher. I think he was a student of Gamow. Pretty sure he was a student of Gamow. And they were detected 20 years later in 1967 by Penzias and Gilson. The main technical issue was since they're so cold, to isolate from background noise. So they managed to do that, and they got the Nobel Prize for that in '78. Now the third, we said that is the primordial abundances of the light elements. We said that all the elements are being formed in stars, except from the light elements. Now, when we had this recombination, we know how the universe, we can calculate quite easily the evolution of the temperature with time. So we know what were the probability of the light elements to form. And the light elements, meaning the first, of course, hydrogen. And then the other light elements would be the helium, lithium, helium-3, etc. And this is something which we can measure. So roughly, for example, we know that the abundance of helium-4 to hydrogen is nearly 1/4. So helium-4 over hydrogen, primordial is 0.245. Or the deuterium over hydrogen, primordial is something like 3.6 times 10 to the minus 5. So these are all elements that were formed during this recombination process that took care in the very early history of the universe. And these are the building blocks of the stars, essentially. And this is something which we can see. And the same
But
for helium-3. Yeah, question?
yes, but does that take into account that there was an equal amount of antimatter that was created with them?
No, that's a different question. There was no antimatter there. There was protons and electrons. Where did the
Because
antimatter go is a great question. Which is not answered.
I see.
We're talking about a universe which was made of electrons, protons, and photons, right? And initially, the photons prevented the production of elements, and because they were scattering too much, but then when they got cold enough, then they could not prevent it, and so the electrons and protons could combine to form the lightest elements. Most of them produce hydrogen, but some of them produce helium, some deuterium, some helium-3, some lithium, and these abundances is something which we can measure. And then the rate of processes which form the heavier elements, this happens in stars, and this is something which we can pretty much understand as well. All right. The fourth I kind of touched, or one of you answered it very nicely. It's the galactic evolution and distribution. So I just mentioned briefly the fact that galaxies are pretty much like living creatures. They age, they're not all the same. They change their morphology. Younger galaxies look different than older galaxies. There are also smaller galaxies attract material as they grow up. And indeed, when we're looking at the very distant galaxies, apart from being redshifted, we're seeing that their morphology is different than the galaxies which are in the nearby universe, namely older galaxies. Galaxy morphologies changes with cosmic time. Do I have anything to say about that? Okay, getting into this is really the subject of a different course, really. The last thing that I want to say is this, what's called the Baryonic acoustic oscillation, BAO. This is something which I'm thinking of whether I should spend the next lecture about that or not. I'll consult with you in a second about that. Essentially, we said that before this recombination, the universe was filled with photons, electrons, and protons. And in this kind of soup, there were waves which could propagate. And some waves, there are these normal modes of the waves. And these waves propagated until the time of recombination, in which case the photons just, were free to go, and they just move freely since then. Now, if you look at the pattern of these photons, they still carry with them these patterns of these baryonic acoustic oscillations, which is something which we can see because it is imprinted on the fluctuations of the cosmic microwave background. So the cosmic microwave background is, I said it's isotropic, and it's very, very true to a great approximation. It's isotropic up to something like 10 to the minus 5. But when you look at the resolution of 10 to the minus 5, you start seeing fluctuations in the cosmic microwave background. And these fluctuations, they initially look random. I actually looked at some, let's see this looks like, yeah. That's how it looks like when you look at the small fluctuations. The scale is about 10 to the minus 5. So the cosmic microwave background looks isotropic, but there are very small fluctuations, and these fluctuations are not exactly random as they seem in first sight. Rather, when you analyze them using spherical harmonics, the YLMs, which I hope that you've learned, then you end up with something like that. There are multiple moments, and these are the CIs on the y-axis. And as you're seeing, they have a very well-designed pattern. There are some tops and there are some dips, and they occur at very specific multiple moments. And they are really imprints of these waves, essentially, oscillations that the baryons had before the decoupling. And that there were waves that simply were propagating in this big plasma. And by measuring this, we can actually measure exactly, this is one of the things that tell us the context of the universe. This is something which, in addition to the measurements of nearby galaxies, these are the ones that tell us how much matter is in the universe, how much radiation, etc. And these small fluctuations are obviously what form the seeds, regions that were slightly higher density using gravitation attract more matter, which essentially formed, increased the gravitational potential that they ended up with the galaxy and the galaxy clusters that we're seeing today. So this can be matched to the galaxies that we're actually seeing today, to, in a statistical way, to the pattern of galaxies that we're seeing today. And of course, this matches. Okay, so this was kind of a very brief, not even an introduction, just a small explanation about the baryonic acoustic oscillations. So all five are independent measurements, and all of them support this idea of Big Bang. All right, I think we're already over time. I'm pretty much done with that. So now we still have one more lecture on Thursday, which I'm kind of thinking to myself, and I can consult with you to see what you would be preferring to do. Let's say we have three options. One of them is to, so first, do you have any questions about anything we said so far? Yes, I strongly urge you, if you have any questions, any issues, please do them now. I want to remind you what I said at the beginning of the lecture. I would accept exercises until the end of the month, not after that. If you, but of course, so if you need any extension, that's the maximum that I can give you. But please submit your homework on time. Now, for the lecture on Thursday, you can do a stop sharing now and stop the recording. I really have three options, which